Hi, my name is Muhammad Hamza, and I'm a junior mechanical engineering student here in the U of M. This summer, for my SURE program, I work with Professor Bogdan Epureanu in his Vibrations and Acoustics lab, along with Professor Stefano Zucca, who is a visiting professor from Politecnico di Tourino in Italy. We work on a project called The Dynamics of Mechanical Systems with Nonlinear or Intermittent Contact. Before I delve into the specifics of my project, let me share with you some background information on my research.
A nonlinear or intermittent contact is a type of contact between surfaces that can exist in three states in a period where it is excited, or when a force is applied to the structure containing intermittent contact. The three states are no stick, slip, and stick. It is considered a nonlinear behavior since the area of contact changes. Below is a diagram showing a 1 degree of freedom spring mass damper system which incorporates intermittent contact. There is an initial gap which shows no stick, and when a force is applied, the mass will move towards the other spring, and there will be a stick. And when the mass is pushed back, there will be a slip, and the cycle continues. Knowing how intermittent contact works is really important since the phenomena can be found everywhere. For example, it can be found in joints and cracks. For engineers, the ability to accurately simulate them is crucial. Knowing how systems with intermittent contacts respond during operation will bring in systems that are less prone to damage caused by resonance, have a longer lifespan, and will not fail easily. In other words, with better systems, it would save money, save lives, and make the world a better place in a way. However, like other nonlinear phenomena, it is very difficult to simulate systems with nonlinear contact. For linear systems, simulations are done using their finite element model, in which we can easily obtain their modal properties and response levels to excitations. For nonlinear systems, obtaining the same information would take a long time, since solving nonlinear equations require approximation of the solutions through iterative schemes. Over the years, researchers and engineers have made progress in this field by creating new methods to simulate nonlinear dynamics more efficiently. Thus, Professor Epureanu and Professor Zucca have created a technique using bilinear modes to solve nonlinear cases, particularly with piecewise linear oscillators. The idea of this method is to represent spatial coherences in system dynamics using two sets of normal modes, hence bilinear, with special boundary conditions. This method is faster than the current one, able to solve cases with intermittent contact, even if friction and pre-stress was included. This crack plate was used as a test case for this method. The intermittent contact of the system takes place at the crack. The two boundary conditions are fixed and free. Fixed constrains the crack to have no relative displacement in plane, while free removes the constraint. Modes are essentially the form of the model at a certain frequency, obtained through model analysis. To illustrate modes, here is an animation that shows the first mode of the model using a free boundary condition. Over the summer, I developed a mode selection algorithm that selects modes based on a certain condition. These modes are used as input to the solver that uses the bilinear modes method. This algorithm picks modes which are responsible for the responses of the model when force is applied to it. Responses are the vibrations of the model. This algorithm also helps reduce calculation time and tell users which modes are important in making the model vibrate. By using the mode selection algorithm, the solver managed to obtain a result that has only 0.05% error compared to the result obtained by using another current method, which happens to be our benchmark for the bilinear mode solver. This shows that the algorithm has selected the right modes. Currently, we are testing the bilinear mode solver on more difficult cases so that we could perfect it and finally make it usable for any cases of intermittent contact. I would like to thank the U of M, Professor Epureanu and Professor Zucca for giving me this great opportunity to do research.